Today, on how it's made. Decorative sombreros. Salad dressings and marinades. Cap guns. And regenerative medicine. The sombrero is a traditional Mexican hat with a large brim that's designed to cast a wide shadow over the face and shoulders. Everyday sombreros are made of straw, but mariachi bands and other folkloric performers wear fancier ones made of velvet, wool, or felt with elaborate decorations. These fancy sombreros are produced primarily as decorative tourist souvenirs. Artisans construct and decorate each one entirely by hand. They start by positioning a sun-shaped cutting die at the center of a large sheet of thick paper. As the press closes, the die slices through, making a hole. Next, they sandwich the sheet between two fiery hot sombrero-shaped forms. These mold the paper to the shape of the hat's brim. They trim off the excess and stitch the perimeter to reinforce the edge. They soak the brim in a gelatin solution and lay it out in the sun to dry to stiffen the paper. They fold a sheet of paper and die cut another shape. They sew the far ends together to form a circle. This will form the top of the sombrero, called the cup. They spread glue along the base where it attaches to the brim. They also apply glue to a paper circle. Then they place the cup on the same hot form they used to mold the brim. After shaping the cup, they reinforce the top with the paper circle. The sombrero is now fully constructed. The next step is to cover it in fabric. They coat the surface with glue, then, section by section, adhere pieces of velvet or felt. They start with the cup. The fabric has been pre-cut and sewn to the correct shape. The next section is the brim's underside. They trim off the excess fabric with a razor blade and cut away the fabric over the cup. Next, a piece to cover the top of the brim. Throughout the fabric application process, he's careful to pull the material taut and smooth it down. A final trimming, and the sombrero is fully covered. Elsewhere in the factory, automated machines weave spools of polypropylene string and metallic plastic string into colorful trim. Artisans in the decoration department cut out paper motifs and cover them in trim. Then they make colorful appliques by sewing the motifs and sequins onto velvet-covered paper shapes. They glue these appliques onto the sombrero. Finally, they glue trim where the applique edges and hat surface meet. This holds the edges down and finishes them off nicely. On pricier sombreros, all the decorations are sewn by hand, no glued-on appliques. The artisans complete every sombrero with the fabric lining in the cup, then an under-the-chin drawstring, handy for wearing or hanging this Mexican memento. Supermarket shelves are stocked with a vast selection of tasty ready-made salad dressings and marinades. Dressing adds instant pizzazz to salad, whereas marinade flavors and tenderizes raw food by slow penetration over a few hours prior to cooking. Salad dressings can be cream or mayonnaise based, or oil and vinegar based. This particular line of dressings and marinades is made entirely of certified organic ingredients. It's also gluten-free and sugar-free for those with celiac disease or diabetes. While the salad dressing's base stays much the same, the seasoning ingredients vary to create different flavors, such as the one we're about to see being made, sun-dried tomato and garlic vinaigrette. On the production floor, they start by heating water, then adding tomato paste. Next, they add dried basil. They pour all ingredients directly into the vortex created by the mixing blade to ensure thorough blending. They add sun-dried tomatoes, minced garlic, and salt. After 15 more minutes of mixing, they add soybean oil and extra virgin olive oil, both expeller pressed, meaning extracted from the source using a mechanical press and not the conventional chemical process. The last ingredient is gluten-free red wine vinegar. Whereas the oils provide both taste and texture, this vinegar produces a full-bodied flavor. Cooking another 20 minutes or so on high heat stabilizes the product, giving unopened dressing a shelf life of up to a year. On the bottling line, a machine called the inverter flips the empty glass bottles upside down. Then from underneath, an air nozzle shoots in a blast of filtered air. This loosens any dust or dirt particles inside the bottle, enabling a vacuum to then suction them out. Another inverter flips the bottles right side up again as they enter the filling machine. Exiting the filler, the bottles pass through a machine which dispenses plastic caps. Then, with a row of spinning discs, twists them on. Finally, a tamper-proof seal and labels. The marinade production process is much the same, but with different ingredients, of course. This batch is sesame teriyaki flavor, of which a key component is gluten-free tamari, a Japanese soy sauce made without wheat. Again, the process begins by heating water in a cook kettle. They pump in tamari, pour in salt, then powdered ginger. Next, minced garlic and sesame seeds. Then, agave nectar, a natural sweetener that's low glycemic. They add pureed ginger. Then expeller-pressed soybean oil mixed with xanthan gum, a natural thickener. About 20 minutes cooking on high heat, and the sesame teriyaki marinade is ready for bottling. Like before, the glass bottles undergo a vacuum cleaning en route to the filler. There, pistons suck up the marinade like a syringe, then inject it into the bottles. The filled bottles go through the capper, then travel on a conveyor belt to the next machine, which slips a plastic neckband over each cap. A shot of hot steam shrinks the neckband tightly around the cap, creating a tamper seal. Finally, The labeling machine applies glue to the back of a paper label, then wraps it around the passing bottle. Besides flavoring and tenderizing raw food before cooking, you can also pour marinade over meat, fish, or vegetables while cooking. A surefire way to let the gourmet out of the bottle. A cap gun is a toy revolver which, when you pull its trigger, makes an explosive sound like a gunshot and emits a small puff of smoke. The caps, tiny dots of gunpowder on either a plastic ring or a strip of paper inserted in the gun, produce these realistic effects. Cowboy-style cap guns were the rage in the 1950s and 60s during the golden age of westerns. This small American factory uses the molds the major toy companies of the day discarded when they stopped making cap guns long ago. Caps are little dots of gunpowder about 1.5 millimeters in diameter sandwiched between two strips of paper. Pulling the trigger releases a hammer, which strikes the cap, exploding it. This injection molding machine makes the grips, the faces of the gun handle. It shoots hot liquid plastic into 10 grip molds simultaneously. The plastic cools and solidifies in just seconds. The color and design of grips vary by model. The ones on this rancher-style cap gun feature a steer's head. The rest of the gun is made of cast zinc. Workers load a zinc bar into a smelting pot heated to about 400 degrees Celsius. The bar melts within a couple of minutes. The molten zinc travels through heated pipes to a plunger, which injects the zinc into a gun parts mold. The zinc takes just 10 seconds to cool and harden. Then it's just a matter of separating the parts. The gun's main body, which contains the right side of the barrel, the loading gate, which covers the cap box, the cylinder, the left side of the barrel, and toy bullets, which load into the cartridge but don't shoot out of the gun. The trigger and hammer are cast in a separate mold. Every piece has flashing, excess metal that forms in the gap between the two halves of the mold. After removing as much as they can with pliers, workers file down the rest. Some flashing is quite thick, so they use a sander to remove it. Workers rinse the smoothed parts in acid to clean the surface, then electroplate them with zinc. They dip the parts in a clear liquid coating to make the matte surface shiny. Now assembly can begin. First, they install the spring which opens the loading gate. They take the left side of the barrel, add the latch that holds the loading gate closed, and the spring which puts tension on that latch. Then the cylinder. And finally, the guiding disc, which turns the cylinder when you squeeze the trigger. They screw all that to the main body, which contains the right side of the barrel. They insert an orange plastic safety tip into the end of the barrel. Laws require this to prevent cap guns from being mistaken for real firearms. They hook the loading gate spring to the gate's latch to hold it closed. Then they install the hammer spring and hammer. Two brass grommets secure the cylinder turning arm and the pusher, which feeds the caps one by one out of the cap box, into striking position. The trigger spring keeps tension on both the cap pusher and the trigger. Next, they install the loading gate. After hooking up additional springs, workers attach the top part of the hammer spring to the holding pin on the hammer. Then the bottom part of the hammer spring to the holding pin on the frame. Finally, the plastic grips. One for each side of the gun handle. Being cast from vintage molds, these cap guns feature intricate scroll work, a degree of craftsmanship rarely seen in toys nowadays. Something perhaps better appreciated by the parents of the Wild West cowboys than by the pint-sized gunslingers themselves. When parts of the human body break down or are damaged, options are limited. Scientists are working on providing replacement parts on demand, like fingers, ears, and bladders. Laboratory-engineered bladders have already been successfully implanted in humans. The stuff of science fiction may soon be a reality. They begin with a mold, a finger mold on the right and an ear on the left. These molds can be made of synthetic polymers or natural materials such as collagen. Scientists will grow real cells on the molds. To obtain those cells, a scientist first extracts a small piece of cartilage, which is a type of connective tissue in the body. She chops it into little bits. She transfers the minced cartilage to a test tube, partially filled with a special enzyme. This enzyme dissolves tissue, leaving only the cartilage cells. She then places the test tube in a centrifuge for a high-speed spin. This causes the cartilage cells to separate from the enzyme solution and settle on the bottom. She siphons off the liquid and the tiny cells remain in the test tube. Next, she adds a red liquid. It's a culture medium. It will act as a fertilizer to stimulate cell growth. Transferred to a Petri dish, she swishes the mix to disperse the cells. Then it's into an incubator warmed to 37 degrees Celsius, body temperature. It's the perfect environment to spur more cell growth. Meanwhile, a computer-controlled machine builds the mold of the ear. It layers synthetic polymer to produce an authentic-looking shape. This process takes about 5 hours. In the meantime, the microscopic cells have multiplied 20 times. The scientist drips them onto the completed mold, where they continue to grow. In the future, cell-covered ear molds could be implanted under a patient's skin. Cartilage would form, and the body would accept the part as its own. Other scientists are working on growing blood vessels and heart valves. They start by extracting a type of stem cell from human blood. The researcher first fills a test tube with a clear, high-density solution. He adds diluted blood to the clear solution. Almost instantly, the different components of the blood begin to separate. The heavier red blood cells plummet, and the lighter stem cells rise to the top of the test tube. A spin in the centrifuge leaves the components visibly separated, allowing scientists to retrieve the desired cells. They'll convert them to endothelial cells, which line the inside of blood vessels and heart valves. In the meantime, they construct the blood vessel mold. The scientist adds solvent to liquid collagen, causing it to instantly dissolve. He adds little white beads. They're synthetic polymers. And they liquefy over a period of about an hour. They spray the collagen concoction onto a rod that spins as a carriage moves it to and fro for even coverage. The collagen and polymer mixture quickly solidifies around the rod. The scientist slides off the now hardened biomaterial. He has a mold for shaping a human blood vessel. He coats the mold with the microscopic endothelial cells, which by now have grown and multiplied. He then pumps fluid through it to simulate blood flow. This conditions the cells to go with the flow and collectively operate as a real blood vessel. To grow a heart valve, they don't actually build a mold. They use a real valve from a pig. The scientist plunges the pig valve into a container filled with a mild detergent. It goes into a machine that shakes it up. The agitation helps scrub off all the cells, leaving only the valve skeleton. He saturates the valve skeleton with human cells, where they grow and thrive. The research team then pumps fluid through the valve, just like they did with the blood vessel. This trains the cells to do the work they would need to do in the human body. Even Dr. Frankenstein would be impressed. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitsmade.com.